15 kilometers below the Earth's surface, something is about to happen. Mother Nature is pissed, and she's about to get medieval on the crust. This is an earthquake. But it ain't over until the fat lady sings, and the fat lady demands aftershocks. Before we can begin to understand aftershocks, we should first attempt to understand earthquakes themselves, because an aftershock itself is nothing more than a specific type of earthquake. Here we see a map of the plate boundaries on Earth. These plate boundaries are marked by large amounts of seismic activity. Almost all earthquakes occur along plate boundaries. An earthquake is said to occur when sudden slip on a fault releases stored elastic energy and radiates seismic waves. Almost all earthquakes occur along plate boundaries. This cross-section shows three types of plate boundaries: convergent, divergent, and transform. The two sides of these boundaries move relative to each other and produce earthquakes. This is described by a theory proposed by Henry Reed called elastic rebound theory. During what is called the interseismic period, two plates move past each other except at the fault where they are stuck together. This process increases the elastic strain energy in the rocks until there is too much energy and the fault breaks to relieve all this built-up stress. The breaking process is the earthquake, and relative to the interseismic period occurs almost instantaneously.
Aftershocks are earthquakes. In areas where earthquakes occur, there is what's called a background seismicity rate. This is the rate of small earthquakes that are usually undetectable by human senses, but can be picked up by seismometers.
We define an aftershock to be a specific type of earthquake that follows a larger earthquake and has general spatial and temporal characteristics.
One general feature of aftershocks is their temporal evolution. This is described by Omori's law, named after Omori. This tells us that the rate of occurrence of aftershocks decays with time until it comes to the background seismicity rate.
Omori's law is an empirical relationship that describes the temporal distribution of aftershocks. The rate of which aftershocks occur will decay linearly with time. This graph serves to illustrate the decay with time of the number of aftershocks. If at a time 0.1 seconds after the main shock, 100 aftershocks occur, Omori's law tells us that 1 second after the main shock, 10 aftershocks occur, then 10 seconds after, 1 aftershock occurs, and so on.
We can also describe the size distribution of aftershocks. This is known as Bath's law, named after Bath. This tells us that on average, for any given main shock magnitude, we have one aftershock of the next magnitude down. For example, if we had a magnitude 7 main shock, we would have one magnitude 6 aftershock. After this, the earthquakes appear to follow what is called the Gutenberg-Richter distribution, named after Gutenberg and Richter, and this tells us that if we were to have 1 7 main shock, we would have the 1 6 aftershock, and 10 5s, and 100 4s, yes, this is correct, and 1,000 3s, and so on.
The spatial distribution of aftershocks is most likely due to small changes in stress caused by the seismic slip of the main shock. Earthquakes redistribute stress in the crust. In some areas, slip from an earthquake will increase stress, and in some areas, stress will decrease. A main shock ruptures a large fault in what is called the fault zone. The fault zone is made up of a distribution of smaller faults. It is these smaller faults that may slip by the stress changes and produce what we call aftershocks. Here we see stress changes from earthquakes greater than magnitude 6 in southeastern California from 1979 to 1992. The white dots are earthquakes that occurred within 25 days of the lander's main shock. Regions of increased stress are regions of warm colors, and regions of decreased stress are cool colors. As you can see, a majority of the lander's aftershocks occur in regions where the stress has increased.
Yes. Coca-Cola, McDonald's, Pepsi. Flurgny, in the big flurgner, be sniffner,
Phillip Rivers passes the ball to LaDainian Tomlinson for a touchdown.